In this video series, we're discussing the general linear model. We call the general linear model general because it applies to all of the types of designs that we have looked at in this course. We call it linear because we're looking at a combination of effects that are summed together. And we're calling it a model because we use this combination of effects to model or predict a response outcome. What I'm going to talk about in this video are the common analysis principles that unite everything that we do when we're analyzing data using the general linear model. And I will return to the one-factor randomized design that I've already shown you the linear model for in order to exemplify these common analysis principles. So the first thing is that the assumptions that we make, that is the conditions that are necessary in order to make valid inferences, are for the error term or the residual. For the residuals, we need them to be independent of one another, and we achieve that by making sure that our participants are independent of one another. We need the residuals to be normally distributed. We typically look for a normal distribution using a QQ plot. And then we need sphericity. Now, I've only used the term sphericity in the context of within subjects designs, but sphericity is really a general term that stands for homogeneity of variance. The question is, do we need homogeneity of variance of our individual observations within our groups, or do we need homogeneity of variance in terms of pairwise differences? The first is for between subjects designs, the second is for within subjects designs, but all of those lumped together can fit under the umbrella of sphericity. So sphericity is really a generalized homogeneity of variance. And it is that sphericity term that is different for between subjects factors than for within subjects factors. Again, in between subjects factors, we just need homogeneity of variance of our conditions, whereas within subjects factors, we have to take all the pairs of differences and look for homogeneity of variance among those pairs. In both instances, we would achieve sphericity. We look at the same conditions for valid inference for factors of the same type. So all of the conditions for between subjects factors apply to all of the factors that are between subjects. Similarly, all of the condition for a within subjects factor are applicable to more than one within subject factor if we have two or more within subjects factors. So really, we need to simply break these conditions down into two parts. And really, we're only breaking them into two parts in terms of how we're interpreting sphericity, whether it is homogeneity of variance across conditions or across differences in conditions. Each factor in our model can be analyzed using planned comparisons or an omnibus test and post hoc analysis. The omnibus test is a test of the null hypothesis that there are no effects for that particular factor we're studying. And if there are no effects for that particular factor we're studying, then we hope not to reject the omnibus test. But of course, we may not reject the omnibus test because we don't have enough power. In either case, whether it's because there's no effect or we don't have enough power, if we do not reject the omnibus test, there's no sense in going on to post hoc analysis. We only do post hoc analysis when we're able to determine that there are omnibus effects. We can forgo the omnibus effects and look at planned comparisons if we choose. In the previous video, I introduced the one-factor randomized design and model in which subjects are randomized to J different experimental conditions. And the linear model is the model you see here, where we're looking at the response for person I in condition J as a linear sum of the baseline, that is the mean, the effects of being in that particular condition, and then what's left over, that is the error or residual for person I in condition J. Let's look at the common analysis principles that I just presented in the context of a report that I constructed and went over with you in a previous video just to see how those principles are applied. This is a one-factor design. Now note, it is not a randomized design. So whenever I give you the linear model for, say, a one-factor randomized design or any kind of design in which I have the word randomized, you can take out the randomized and the model does not change. The model is the same. So this is a one-factor design or a one-factor observational design, you could call it. That means that we did not put people into conditions. They were rather naturally, inherently, or previously assigned to those conditions before we began the study. The linear model stays the same. So in this particular case, looking again at our linear model, we are wanting to know if the person's view of risk of riding on an airplane, that would be the Y, is equal to the sum of the mean risk across everyone in our study, plus the effect of being in that particular worldview condition, plus what's not explained by the first two components of this model, that is the leftover, and that would be our residual. So that linear model will apply to this case right here, even though we did not randomize to conditions. Remember that the errors are what we have to look at if we want to make inferences. Now, anything that you do in order to estimate effects is valid regardless of whether or not you can make inferences. So those assumptions or conditions for valid inference are just for valid inference. They're not for descriptive estimation. You can describe and you can estimate effects without making inferences. But in science, we typically don't want to know what just happens in a single study. We want to be able to establish common or general principles outside of the study. So that is why we went through this process of looking at the normality of the residuals. Now, the first condition was that we have independence. What about that? Well, that's in the design of the study. You can't see that in the statistical analysis. So I need to hope that when Karlstrom, Woodward, and Palmer did this study, that they were taking individualists who were independent of one another, hierarchicalist independent of one another, and egalitarian independent of one another. Furthermore, because those participants are in one and only one group, either they're individualist or hierarchicalist or egalitarian, not in two groups or all three groups, these become independent levels of a single factor worldview. And because they're independent levels of that factor, this is called a between subjects factor. And so if I think about the between subjects factor in terms of sphericity, that simply means homogeneity of variance of the conditions. And that's what I'm looking at in this residual fit plot to see if the various conditions have the same type of variation. I can also look at that in my descriptive statistics up here, in which I looked at the standard deviation of each of the groups. And then the next thing we talked about is how we can do an omnibus test and move on to confidence intervals for our contrast of interest if, in fact, we're able to reject the omnibus null hypothesis. So we can now think of the null hypothesis here not necessarily just in terms of equality of means, because that works for the one factor, but that's a little more difficult when you talk about things like interaction. But rather, we can look at the omnibus null hypothesis is saying there are no effects. All those alphas in our model, all the alphas that we talked about right back here, there are three of them in this case, alpha 1, 2, and 3, for the three different worldviews. We're basically saying that each of those are equal to 0 is the omnibus null hypothesis. And here we're able to reject that omnibus null hypothesis because we ended up with a low p statistic. That allows us to move on into looking at particular comparisons, and that's what I did when I said I did Tukey confidence intervals. So with the general linear model, once we want to move on to inference, We move on to conditions for the error term that are not necessary for description, but they are for inference. And then we use planned comparisons or an omnibus test followed by post hoc. Now, what we did not have in that one-factor design was the potential for an interaction because there was only one factor. And to have interaction, you have to have two or more factors. When we have two or more factors and we put interaction in our model, we don't need to put interaction in our model if we have some theoretical basis or past research that suggests there's no interaction. But when we do put it in the model, the focus is on the interaction. And then if we can verify that it doesn't appear that there is interaction, or if we don't put it in the model, the focus is on main effects, either because the interaction appears negligible when we look at our data, or because we don't have it in the model because we do believe that the interaction is negligible. So whether we focus on main effects or interaction depends upon whether or not we think we have interaction. In the one-factor case we just looked at, again, we cannot have interaction, so we only focused on a main effect. That is the effect of worldview on the perception of plain risk. In the upcoming videos, we'll look at models for the other kinds of designs that we have covered so far in this course.